Hello friends, so in connection with the unit 1, that is electric charge and fields, today we are going to continue with the concept of electric dipoles. What's an electric dipole? As the word suggests, it is made up of two words, dipole. So there are two poles. So here you have two polarities. So what are the two polarities possible? We have two equal and opposite polarities, positive and negative. So a pair of equal and opposite charges separated by a small distance is called an electric dipole. So here, for the sake of convenience, the distance between minus q and plus q shown over here is large over here. But in practice, this distance is very, very small. So such an arrangement is called a dipole. So why we are studying about dipole? Because so far we have learned about what is the effect of point charges, what is force because of point charge, what is electric field because of point charge. So now it is the time to discuss or to study what is the effect of a dipole. That means when the charges are in pair. And why we are learning about it? Because in nature, it is possible that many, you can say, molecules are having dipole. Now, how to measure dipole? So a dipole is measured using dipole moment. Dipole moment measures the strength of an electric dipole, and it is a vector. You can see over here the product of the charge, either of the charge, q, and the distance between them is called the dipole moment. And what is the direction? As you can see over here, the direction is from minus q to plus q. Right? So my direction is from minus q to plus q. Okay, so that's a dipole moment. Dipole moment is a vector. And as you already know, the dipole moment is the product of q into 2a. If it is q into 2a, that means it is supposed to have a unit. So its unit is coulomb into meter. Right? You can very easily find out its dimension also. Its dimensions are whatever the dimensions of coulomb into that you are supposed to add one length dimension. Right? Now, what are natural dipoles? So the dipoles are common in nature. In molecules like H2O, HCl, you can say C2H5OH, CH3COH, etc. The center of positive charges does not fall exactly over the center of negative charges. As you can see over here, the center of positive is over here and center of negative Cl minus is over here. And there is a 0.1 nanometer distance between them. So this is forming a natural dipole. Similarly, in H2O, you can see the center of H plus ion is over here and O minus is over here. So this is the distance between center of the positive charges and center of negative charges. So this is going to create a dipole. So such molecules are electric dipoles and they have permanent electric dipole moments. So in nature, there are many elements, many molecules which are permanent dipoles. And that's why we are learning about the dipoles and the field because of it. Right? Now there is a concept known as ideal dipole. So we know that dipole is a product of, you can say, q into 2a. So if the distance is very, very small, that means if 2a tends to 0 and the charge q tends to infinity, if charge is very, very large, such that the product q into 2a is finite, then such a dipole is called ideal dipole. So obviously, we have to take home the information that an ideal dipole is a very huge charge having very, very small distance between two ideal and opposite charges. Now, in this section, we are also going to discuss about what is the electric field due to electric dipole. So electric field due to dipole is studied in two ways. Along the axis, that is along the line joining the dipole and perpendicular to the line joining dipole, right? So in today's section, today's lecture, we are going to discuss about what is electric field along the axis. So this part is along the axis. So you can see over here the field, the point is along the axis, that is along the direction of the dipole, and it is at a distance r from the midpoint of the dipole. So what is going to be the field at electric this point P is what is to be discussed over here. So we can see over here that individually this is nothing but a point dipole minus q. Charge is also point dipole. So electric field due to point dipole minus q is minus q divided by 4 pi epsilon 0 into r plus a square, and the direction is along you can say the direction of dipole. You can see dipole is given in this fashion. So that's all right. So this is something which is already known to us using Coulomb's law. Now, the second charge, that is E plus Q, is also point charge, and it is going to have offer the electric field in the opposite direction. So it is given by plus Q over 4 pi epsilon 0 into r minus a square, and this is also as per the Coulomb's law. Now, as per superposition theorem, the electric field at point P is vector sum of these two fields. We can find out vector sum of these two fields as EP because of plus Q plus EP because of minus Q. So it is going to be Q over 4 pi epsilon 0 into bracket 1 upon r minus a square minus 1 upon r plus a square. Right? So if you manipulate it, yeah, if you manipulate it, we can pick up Q over 4 pi epsilon 0 common. So r plus a square minus r minus a square divided by is r square minus a square whole square. We can further simplify it mathematically, and we can see over here that this part gets cancelled out. So also gets cancelled out, and we are left with the term Q over 4 pi epsilon 0 into 4AR. Now this in numerator we have Q into 4AR. We can rewrite it as 2 times 2A into Q. 2A into Q is nothing but the dipole into R. Right? We are rewriting so that we can have a meaningful form. So we can now represent it as a 2 times P into R divided by 4 pi epsilon 0 into R square minus A square whole square. And this is a unit vector showing that its direction is along the dipole, which is considered over here, minus Q to plus Q. And P, that is dipole moment, is Q into 2A, which is already known to you. So if this distance R, that means if I have this is minus Q and this is plus Q, this is the dipole, and this is midpoint, and the point which we are discussing is very far. This point P is having this distance R is very far in comparison to the dimension A. We have seen in the natural dimension this 2A is in nanometers, so it is 10 raised to minus 9. This distance is very, very small. So if R is very, very large compared to you can say A, that is distance between the midpoint and the dipole, then we can neglect the A in comparison with R. So in that case, R square minus A square is approximately equal to R square, or R square minus A square is going to be approximately equal to R raised to 4. So in the last expression, if we rather substitute these values, what we can have over here is the axial field is equal to, that is E at point, which is also, we can call it E axial. It is 2P into R divided by 4 pi epsilon 0 into R raised to 4. So R gets cancelled out, and we are left with the expression that E axial is 2P over 4 pi epsilon 0 into R cube. So it is along the direction of dipole moment, and the magnitude is given by this formula, right? So in short, we can conclude that if I have a dipole Then electric field along the axis, along the straight line joining these two charges at any point P, which is at r distance from the center, which is very, you can say, distant from the midpoint, or compared to the size of dipole, the point is very far away, then in that case, E axial electric field is given by 2p over 4 pi epsilon 0 into r cube. And it is directed along the direction of the dipole, that is minus p2 plus q. And in short, we can say that this is the highlight. The axial field is inversely proportional to r cube, right? In general, if you point, you can say point charge, electric field is inversely proportional to r square. But in case of dipole, it is having cube proportionality. So it dies off very quickly. So the effect of minus q and plus q cancel out each other at far distance. So in such a case, the electric field dies out very quickly. This is also commonly asked, you can say short question or MCQ, why electric field dies out quickly in case of dipole. So this is the reason, right? So this is all about the electric dipole and the axial field because of the dipole. In next class, we are going to discuss about the electric field which is at a point perpendicular to the line joining dipole. Right, so we'll continue about the same. I hope you understood this and you like this. Right, thank you.